All right, in our next problem, we're looking at the following. According to Hooke's law, the force required to hold a spring stretched x meters beyond its natural length is given by f of x equals k times x, where k is the spring constant. So suppose that 3 joules of work is needed to stretch a spring from 11 centimeters to 13 centimeters, and another 5 joules is needed to stretch the spring from 13 centimeters to 15 centimeters. Find the exact value of K in newtons per meter, part A, and then part B, we're going to see if we can find the natural length of the spring in centimeters. So just to start with, just a reminder again, we find work done by springs using the formula work equals the integral from A to B, where A and B the bounds are where we're stretching from and to, of kx dx. And here again, K is the same spring constant that we found using Hooke's law. So I want to start this problem by drawing for myself just a little diagram, because I like to go ahead and make some conversions before I start a problem. So first up, if we were to start counting here at 0 centimeters, then my spring is going to have a certain natural length, n. So I'm going to say this is n centimeters. So here will be all the other increments, 11 centimeters, 13 centimeters, and 15 centimeters. And so I'm actually going to start by just converting this to meters. I would rather measure in meters. So we will call this n meters. So this will be 0.11 meters, 0.13 meters, and 0.15 meters. But I also would like to make an adjustment for natural length. So I'm going to subtract n off of each one of these values to get the actual distance that the spring has been stretched. So at the natural length, we have stretched the spring for 0 meters. At the first increment at 11 centimeters, we have stretched this spring 0.11 minus n meters, 0.13 minus n meters, and 0.15 minus n meters. All right, so I'm going to set up the integral that would calculate the work done in stretching from 11 to 13 centimeters. And so that integral, like I said, the problem says that 3 joules of work is needed. So 3 is equal to the integral from 0.11 minus n to 0.13 minus n of kx dx. So actual integration here will give kx squared over 2, and we will evaluate from 0.11 minus n to 0.13 minus n. So I'm going to plug in top minus plug in bottom. Should be very methodical. So I'm going to write this as k over 2 times 0.13 minus n squared minus 0.11 minus n squared. All right, so there's definitely going to be a little bit of cleaning up that's going to be required here. So again, 3 is equal to k over 2. I'm going to FOIL out each one of these binomials. All right, and so when I FOIL out the first binomial, 0.11 minus n squared, with a little bit of cleaning up, I get n squared minus 0.26n plus 0.0169. All right, and we're going to subtract from that 0.11 minus n quantity squared. That will give n squared minus 0.22 n plus 0.0121. All right. Again, I'm going to just continue to clean up. So if we remove our parentheses, I get 3 is equal to k over 2 times negative 0.04 n plus 0.0048. All right, so in this equation, we could solve for either n or k. I think what I'm going to do is I'm going to solve for k. So I get that k is equal to 6 divided by negative 0.04n plus 0.0048. And I tell you what, let's go ahead and box this answer because we will come back and use this in just a minute. Okay. Now, let's calculate the other piece. So the second part of the problem said that 5 joules of work is needed to stretch the spring from 13 to 15 centimeters. So this integral will look like the following. So we will have 5. Oops. We will have 5 equal to the integral from 0.13 minus n to 0.15 minus n of kx dx. And this again is going to be kx squared over 2, evaluated from 0.13 minus n to 0.15 minus n. All right, so again, plug in top minus plug in bottom. So I get that k over 2 is equal to, all right, so this is going to be 0.15 minus n, plug in top, minus plug in bottom, 0.13 minus n, quantity squared. All right, and like before, we're going to go ahead and clean up. So 5 is equal to k over 2. So I will get, for that first binomial, if I go ahead and FOIL, I get n squared minus 0.3n plus 0.0225. And then for the second binomial, I get n squared minus 0.26n plus 0.0169. All right, again, we're going to remove parentheses and clean up. So I get that 5 is equal to k over 2 times negative 0.04n plus 0.0056. And again, here I'm going to solve for k. So if I solve for k here, I get that k is 10 divided by negative 0.04n plus 0.0056. And again, I'll put that in a little box to make sure I can find it, because I'm about to use those two. All right, so since the spring constant k is going to be the same throughout the problem, we know that these two k's are equal. They are the same thing. So we get to set them equal to each other. So if I set both k's in these two boxes equal to each other, I'm going to get 6. I'll make this a little bit bigger. 6 over negative 0.04n plus 0.0048 is going to be equal to 10 divided by negative 0.04n plus 0.0056. All right. Cross multiplication is going to give 6 times negative 0.04n plus 0.0056 is equal to 10 times negative 0.04n plus 0.0048. I'm going to go ahead and distribute. When I distribute, I get negative 0.24 n plus 0.0336 equal to negative 0.4 n plus 0.048. I'm going to rearrange the equation to get all of my n's on one side. So negative 0.24 n plus 0.4 n is equal to 0.048 minus 0.0336. I get 0.16 n is equal to 0.0144, which finally gives n is equal to 0.09. And again, this is still measured in meters. So if you would like to convert this answer, of course, this will be 9 centimeters. All right. So the other part here then, I'm going to go ahead and just kind of put a little partition here so we can keep working. This was actually part B that we found first. We found the natural length. So what is the exact value of K? We can simply plug this value for n back into either one of the two equations that we got for K. It doesn't matter which one you use. I'll use this one right here because it's convenient. So K is equal to 10 divided by negative 0.04. And so we got n to be 0.09 plus 0.0056. And so I get K is equal to 5,000. And this will be newtons per meter. Note that I plugged back in here the n value, that distance in meters, because the problem specifically asked for this K value as a newtons per meter answer.